Hello and welcome to Empowered Learning. This video is the final video in the series on studying spring mass systems by modeling them using second order linear differential equations where all of the constants, all the coefficients are constants. And so in this last example, what I want to do is sort of transition to showing you a force function that does not have the same operating frequency as the frequency of the actual spring mass system. So in other words, we're going to see an example where the natural frequency of the spring mass system does not match the frequency of the force function that's external force function that's being applied to the system. And so the goal of this particular video is to show you what happens whenever we have a force function that's oscillatory, but it doesn't have all the ingredients that we need in order to achieve resonance. Okay, so we're going to see how that sort of changes what our response would be in the different cases where we have no dampening, we're underdamped, we're critically damped, and we are overdamped. Okay. So again, at this point, I've worked several examples, so I'm just going to kind of have this already worked out and just kind of step through it. And at this point, I think if you've been following the rest of the videos, you should kind of get what's going on here. And so I just want to kind of go over the highlights at this point. So if we look at the case where we have this force function, and notice that our frequency for the force function, our omega for the force function here is going to be 1/2 radian per second. Okay, and that's different than the actual response of the spring mass system here. As you can tell with the cosine t's and sine t's here, our natural frequency is going to be 1 radian per second. So what this is telling me is that my force function is operating at a frequency half of what the natural frequency for the spring mass system is. Okay, so if we have no dampening, then of course we've seen many times that the left side of our equation that models it is just going to be 12y prime times 12y. And of course, we could divide both sides by 12 here and just make it y double prime plus y equals sine of t divided by 2. Okay. Now, we know that the homogeneous solution is the same no matter what. So it's just c1 cosine t plus c2 sine t. And if we want to find out what our particular solution y sub p is going to be, we have to compare what our force function is along with our homogeneous solution. And again, we see that since we do not have matching frequencies for the homogeneous solution and force function, then these are not like terms. So these two functions do not possess any like terms. So we can simply just choose our y sub p to be a sine of t divided by 2 plus b cosine of t divided by 2. Okay? And if we take first and second derivatives of those and dump it back into our ODE, so of course that would technically look like this if we did it. And if I divide both sides by 12 to make life a little easier for myself, we'll have this. And at this point, we're actually taking in or putting in what y of p double prime is and what y of p is. And we just work everything out. And we see that we end up getting b is equal to 0 and a is equal to 4/3. And so this portion here, again, is our homogeneous solution or transient response solution. This is how the function, well, really this part of the function is overtaking everything in the short term. In the long term, is our total response is going to act like the particular solution. Okay? Actually, in the beginning, these two functions work together to come up with a total response. But of course, as t approaches infinity, it's going to act more like this one. So what we want to do now is find the natural resonance frequency of the spring mass system. And then we want to find what is the frequency of the force function. Now, of course, we've already addressed that. So we already know that the natural frequency comes from the homogeneous solution, is just 1 radian per second. And the frequency for the force function is 0.5 radian per second. And an actual, let's say the frequency in hertz is just going to be this 1 radian per second divided by 2 pi. Same deal here. It's going to be 1/2 divided by 2 pi. So it ends up being 1/4 pi hertz. So what is going to be the frequency of the homogeneous solution to our spring mass system? And is this frequency the same as the one that we found in example 6b, what we just got through looking at? And so here we know that the frequency of the homogeneous solution is the same as the natural resonance frequency of the spring mass system. Okay, so we know that much. Yeah. So again, just to be clear, we know that whenever we looked at our homogeneous solution here, let's go back. So a homogeneous solution, when we were originally looking at it, is here. Let me go ahead and move this out of the way. So that's what it is. And we see that, of course, the understood ones inside of the sine and cosine arguments are going to be 1. So that is what our natural frequency is going to be. And if we come back here, and it says this is the same frequency that we found in example 6b. And in example 6b, it is that. It is the same exact one. So that's, I'm just trying to connect those two concepts together to make sure that you know that whatever frequency we have for the homogeneous solution is the same as the natural frequency for the spring mass system. So here it says, what frequency would our force function have to have in order to achieve resonance for the spring mass system? And if we achieve resonance, will this system be stable? And what do you think would happen if the system was unstable? Now, of course, we know that our force frequency would have to be the same as the natural frequency of the system. So we would have to have both of these be the same, which in this case, it would have to be 1 radian per second in order for that to happen. Okay. If we achieve resonance, then at that point, our system would not be stable because we already know what that looks like. We actually did that in example 5. Okay. So we saw that we had a y of p that was negative 1/2 times t times cosine of t. And we know because of that particular term in our response, the function kind of grew out of control. Okay. All right. So if we graph this function here, we know that it's going to be stable. And we see here that it's stable. So of course it's, it's bouncing up and down. And because of the fact that you got two functions that have different frequencies that are being added to one another, that's why you kind of see the, the erratic type shape there. But you see it just kind of, going up, going down, going back up quickly, and then going down a lot, and then repeating that process. But it is still stable. It'll just kind of look funny if you actually look at the mass, going back and forth, because it'll go, to the right and then to the left, then quickly back to the right, and then way to the left, and then it'll start that whole process over again. Okay. And so that's what that particular function would look like there. So what I want to do to close us out now is to go and look at the what the graphs would look like for all of these conditions, well, all of these cases rather, where we have the no dampening, the under dampening, critically damped, and over damped for this particular situation when our force function does not have the same operating frequency as our spring mass system's natural frequency. All right, so to close us out here, we're going to look at these graphs again. And so we see with the force function here, we notice that our operating frequency is 0.5 radian per second, or half a radian. And when we look at this, where we have no dampening, this is what our function is going to look like, okay? And of course, we kind of already saw this before, so no surprise there. If we were to add in a little bit of dampening, so if we add in this dampening here, then you notice how, of course, our response, meaning the position of our mass, it doesn't oscillate as far going to the left or to the right, where to the right means our graph here is going up, and to the left means our graph is going down. In addition to that, you see that it's oscillating back and forth slower. And again, that is what we expect whenever we add a little dampening to the actual spring mass system. Okay. Now, in the case of it being critically damped, if we look here, we notice that is getting kind of close to it, and it should be acting that way since 18 is relatively close to 24. So we see that this is what it's going to look like when it's critically damped. And if we look here, notice that our y of p is a sum of sine and cosine functions here. Same deal here, okay? But of course, we know that 2 over 25 and 16 over 25 here is a little less than 2/3. So that's why you see it going down some more, which means that it's oscillating less. But we see that over time, it's going to look like these sum and/or difference of cosine and sine functions here. And this portion, the oscillations times the exponentially decreasing function will kind of fade out and will just act more like this one. Same deal here. It'll try to act like an exponential plus a exponential times a linear function. But again, all of that will fade out over time, and it'll just essentially act like a sum of sine and cosine function. And then, of course, in the overdamped case, again, is going to start off acting exponential. So we see the graph trying to act exponential, but because we have that force function there, it is going to settle out. And even though we do have a high viscosity, relatively speaking, in our dash pod, it's still going to the mass is still going to oscillate back and forth, pretty much at a steady pace, and that's modeled by this particular function here. Okay. And one of the things I wanted to show you here is we see the case. I wanted to compare whenever we have this case here versus this case. Let's see. Yeah. So this case here. And the point that I'm trying to make is that for the critically damped case here, when is going to be the switch off to where this difference of sine and cosine functions here takes over this, okay? So I'm going to cut these off, cut these two on here, and we see that our red function here, which is this first big term in our critically damped response, we see that it's acting exponential. We also see here we have the second and third terms sine and cosine functions. And we see that right here at about 2.5 seconds is when our difference of sine and cosine functions takes over, meaning that the displacement of it is more than the e raised to the negative t times 1 plus t. So if we now click on our critically damped graph, we'll see that at right around this point here, right around here, is when this graph starts to act more oscillatory and less exponential. Okay, and then of course you see as time goes on, it kind of follows the same profile as this function here. Okay, so of course if I turn this off, you'll see that just like that, and if I turn that off, you'll see that it's essentially following that profile after about 7 or 8 seconds. So this concludes our study of spring mass systems. For those of you that watch all of these videos, thank you for hanging in there. It was a lot to cover, but hopefully you have a very good understanding of how these particular spring mass systems work, what their responses look like on a graph, what the concept of resonance is, and as well as how all of this is applied to second order linear, homogeneous, and non-homogeneous equations where all of the coefficients are constants.